start. Today's topic is amplification by stimulated emission. So, recall that in the last class we discussed about rates of emission and absorption, rates of emission and absorption. And in particular we discussed about the rate of spontaneous emission, and we have got an expression for spontaneous emission that RSP of nu is equal to A into rho of nu, density of states, into Fe of nu, where Fe of nu is the emission probability of emission. We substituted the various parameters, that is for rho of nu we substituted the density. So, we have 1 over tau r, I am just recalling, this is recapping. So, 1 over pi h cross square into h nu minus E g to the power half into, we had shown that this is approximately F e is e to the power minus h nu by k t, and then we wrote this in the form of twice m r, there is an expression here, twice m r to the power 3 by 2, and we wrote this in the form of d 0 into h nu minus E g to the power half into e to the power minus h nu minus E g by k t. And then I had shown that the variation looks something like this. So, what I have plotted is RSP of nu, spontaneous emission spectrum, as a function of h nu, and it starts at E g, and then we could find out the peak value. The peak value corresponds to E g is plus half k t. The peak of spontaneous emission occurs at energy value E g plus half k t. I had also asked you to find out the full width at half maximum. So, you can find out the full width at half maximum. So, if this is the maximum, then half of it, there you drop down and find out what are the corresponding values of h nu 1 and h nu 2, and therefore, you can find out the bandwidth corresponding to this. So, corresponding to the frequency here, so we have, let us say this is this point here is h nu 1, and this end here is h nu 2, then we have h nu 1 minus h nu 2, h nu 1 minus h nu 2 by k t, h nu 1 minus h nu 2. So, this is h nu. So, h nu 1 minus, all right, let me, I have written that just as h nu. So, h nu 1 minus h nu 2, and therefore, from this we can find out what is delta nu equal to nu 2 minus nu 1, and once you know delta nu, you can find out delta lambda, that is the line width delta lambda is equal to lambda square divided by c, just a minute. So, nu is equal to c by lambda, and therefore, delta nu is equal to c by lambda square into delta lambda with a negative sign. So, delta lambda is equal to lambda square into delta nu by c. So, we have I had given an exercise to find the delta lambda. So, I had written an expression that show that delta lambda is approximately equal to 1.45 into k t into lambda p square, approximately equal to. So, here k t is in electron volts and lambda p and delta lambda here are in micrometers, in this expression. Here I have a graph. I have actually plotted this function. I hope you can see this. you may not be able to read it. I have a slightly bigger one. Let me put a slightly bigger one. This is too small. Let us see whether this comes out. Yes. So, what I would like you to see is this is actual plot. I have been qualitatively showing you here the variation like this. So, what I have plotted is RSP of nu. I have defined x as h nu minus E g by k t. Then the expression for RSP becomes RSP equal to d into x power half. So, you can divide by k t to this, and there is already a k t. So, e to the power of minus x, and if I divide by square root of k t, this is x power half, and k t to the power half has been absorbed in this d naught. So, RSP can be written in this form with x is equal to this. So, this is a plot of RSP versus x. So, you can see where the peak occurs. So, the peak occurs, these are actual numbers calculated plotted by the computer. So, you can see that xp, the peak occurs at 0.5, xp is 0.5, 0.5. So, h nu minus E g, h nu minus E g by k t equal to half. This implies h nu is equal to h nu p is equal to E g plus half k t, as I had written earlier here. So, the point is actually this shape is really you get a shape like this, and how you can find out at half the maximum value, you find out what is the value of x here and what is the value of x here, and find out the difference between them to find out the delta lambda, line width of a given source. The equation cannot be solved analytically, you have to numerically solve, or graphically you can obtain the solutions and get the expression. So, today I will start with the rates of stimulated emission and absorption. Please try to do this exercise and put some numbers and see what is the line width that you get. Because I had drawn qualitatively the spontaneous emission spectrum, but you can see that if you plot that function, you get indeed a shape which is like that. So, today we will discuss rates of stimulated emission and absorption. Our objective would be, given a piece of semiconductor, a beam of irradiance I nu, of frequency h nu, of energy h nu greater than E g, a beam of h nu here, a light beam of irradiance I nu entering this semiconductor here. What is the material property, effect of the material property on the beam? That is the output here. If I call this as L equal to 0, let us say this is the z direction of propagation, this is L equal to 0 and this is L, length of the semiconductor. What is, if this is the input, I nu of input, then how is I out of nu related to I in? Whether there is attenuation, amplification or no change. Under what conditions, our specific objective will be to determine under what conditions we will get amplification, and what happens in thermal equilibrium, how does the semiconductor behave. So, amplification, if we are looking at amplification, amplification can take place only by stimulated emission, because that is the basic process of amplification, basic process of stimulated emission, where you have one photon which is incident here leads to generation of two photons in simple terms. So, h nu here and gives out. So, this is a process of amplification. Amplification refers to coherent amplification. It is coherent amplification. So, stimulated emission is the one which is responsible for amplification. You can have, if the by the process of absorption, the photon can get absorbed and the output can get diminished or attenuated. So, we want to find out what is the coefficient of gain or coefficient of loss in this semiconductor. That will be our objective. So, let us consider, so let me draw this diagram again. So, this is a piece of semiconductor. So, a light beam is incident at z equal to 0. So, this is the direction of propagation is the z direction. So, z direction. So, this is at z equal to 0. If I consider a small volume element, that is, I consider a small slice of this here, an infinitesimal, a slice of infinitesimal thickness. So, this is z here and this is z plus dz. In the 2D picture here, let me draw in the 2D picture. So, radiation is entering from here. I have considered a small slice here. So, this is z equal to 0 and this is z equal to L, this end, and we have considered z at some position z and z plus dz. Let S be the area of cross, this area of cross section of. So, we want to get an analytical expression. So, let S be the area of cross section of this surface, and the beam is entering through this surface everywhere, the beam is present everywhere in the cross section. So, S is the area of cross section. If I consider this small volume element, and we know that the rate of stimulated emission at a frequency nu is equal to B into rho of nu into F E of nu into the energy density u nu. Rate of stimulated emission is equal to the Einstein coefficient, joint density of states, probability of emission and density at nu, energy density u nu, and rate of stimulated absorption or simply absorption is equal to B into rho nu into absorption. So, probability of absorption into u. Both stimulated emission and absorption depend on the energy density of the radiation u nu. If I look at that small volume element, I am now focusing on the small volume element. So, let me draw the volume element here, that small slice. So, this is of thickness dz. So, z and z plus dz. The number of stimulated transitions, stimulated emissions, so let me write emissions, stimulated emissions per unit time in the volume element S dz equal to rate of stimulated emission is this much. What does this mean? This tells you the number of stimulated emission per unit time per unit volume. Why unit volume? Because density here rho nu is per unit volume. So, this is number of emissions per unit time per unit volume. Therefore, number of emissions per unit time in the volume S dz will be equal to R S T. We are considering at the frequency nu into S dz. So, every stimulated emission, generates a photon of energy h nu, and therefore, energy generated, please see the logic, energy generated per unit time in the volume element S dz is equal to, what will that be? This is the number of emissions, therefore, energy will be equal to multiplied by h nu, because every emission brings down a photon of energy h nu, therefore, multiplied by h nu. This is the energy generated in this volume element. There is a radiation of energy density u nu present, and therefore, similarly energy absorbed, I can find out number of absorptions per unit time in the volume element S dz will be R A B into nu into S dz. S dz is the volume, and therefore, energy generated here because of emission, because of absorption, energy which will be absorbed or energy lost. So, energy absorbed per unit time in the volume element S dz is equal to R A B into S dz into H. Therefore, net energy generated per unit time in the volume element S dz is equal to R S T minus R A B. This is generated and this is generated, this is absorbed. Therefore, the net generated is equal to S dz into H. Okay. So, net energy generated. I want to relate this energy generated to the intensity. So, I nu is the intensity or irradiance of irradiance is energy flux per unit time. This is energy flux, means energy per unit area per unit time. It has the units of intensity because energy flux is energy per unit area per unit time. Energy per unit time is power and power per unit area is intensity. That is why it is I. Energy flux, energy per unit area per unit time, energy per unit time is power and power per unit area is intensity. So, if I knew of Z, if I knew of z is the irradiance on this plane. So, let me show this end plane as plane x and the other plane at the other end as y. So, energy entering per unit time. So, energy entering per unit time per unit time into the volume element is equal to I nu of z, that is the irradiance on the plane z, plane x, I nu of z into the cross sectional area. Energy entering per unit time is intensity into cross sectional area. S is the cross sectional area of this surface. So, I nu into z. What is the energy leaving from the other side? Energy leaving the volume element, S dz, volume element S dz at y, that is at the plane at x plus at z plus dz, on the plane y at z plus dz on the plane y, from the plane y at that plane is equal to I nu of z plus dz into S. I is the intensity or irradiance and multiplied by the surface area tells you the energy entering, energy leaving. Therefore, the net energy generated in the volume element per unit time is equal to what is leaving minus what is entering. So, I nu of z plus dz minus I nu of z into S. Please see this. Net energy generated in the volume is this much, RST minus RAB into SdZ into H2, and net energy generated in terms of intensity is this much. So, they are the same. So, equating 1 and 2, equating 1 and 2, I nu of z plus dz minus I nu of z into S is equal to RST minus RAB into SdZ into H. We have considered an infinitesimal volume element. Therefore, I can write this I nu of z plus dz as I nu of z plus del I nu by del z into dz, where dz is the thickness of this minus I nu of z. Into S equal to this. So, this is equal to del I nu by del z into S dz equal to or. So, this goes off, we have d del I nu by del z is equal to r s t minus r a b into h. Substitute for RST and RAB and we should get the expression. So, RST, so this is equal to B into rho nu into U nu into F E of nu minus F A of nu, F E of nu minus F A of nu, this portion into H nu, into H nu. How is I nu irradiance related to energy density? U nu is equal to I nu divided by velocity. U nu is equal to I nu by velocity. This is energy density. You can see energy per unit volume. And what is this? This is energy per unit area per unit time. So, you can dimensionally immediately you can see that they are, yes, they match dimension. If I nu is the, you can show this, let me write this to you, show that U nu is equal to I nu by V. Just use the base for fundamental definitions of U nu and I nu and show that U nu is equal to I nu by V. So, this is equal to, and what else do we have? We know that A by B, the relation between the Einstein coefficients is 8 pi h nu cube divided by h nu cube divided by V cube. See if it is in free space, but if it is in the medium it is V, that is C by N, where A is equal to, therefore, B is equal to A is 1 over tau r, therefore, we have V cube divided by tau r into 8 pi h nu. So, this is the coefficient B. Einstein coefficient B is, we have used A by B is equal to 8 pi h nu cube by V cube, therefore, B is equal to this. So, we substitute there here in this expression. So, let me substitute here. So, V cube divided by 8 pi h nu cube into rho of r, rho of nu into tau r, radiative recombination time, into U nu, which is I nu divided by V, velocity, into F E of nu minus F A of nu. It is a very simple derivation, but for the sake of completeness, let me not skip any step and show you. So, 1 h nu goes here with this h nu, 1 h, and this becomes nu square, and 1 v goes here with this, and therefore, we have del I nu by del z is equal to v square by 8 pi nu square, this v, or I can write C by n, into rho of nu by tau r into F E of nu minus F A of nu intensity is a function of z. Please see, this here does not depend on z, independent of z. Intensity I enters the medium, and depending on the position z, it may be getting attenuated or amplified, whatever, but I is a function of z. And therefore, since I is a function of z alone, I can write this as di nu by dz is equal to this whole coefficient here. It depends on the frequency. Therefore, I call this as gamma 0 of nu in I nu of z. So, what is the solution? This gives, or I nu of z is equal to I 0 of nu, or I nu of 0, that is the entrance at the entrance point, into e to the power gamma 0 of nu z. We have got an expression for any value for the intensity at any value of z. If you are looking at the output, so this is z equal to 0. If I 0, I nu of 0 is the intensity here, at the output at z equal to L, this will be I nu of L is equal to I nu of 0 into e to the power gamma into L. So, I nu of L or I nu of z will be greater than I nu of 0 if gamma is positive. If gamma is positive, then I nu of z is greater than. When will gamma be positive? So, this tells that there is amplification. So, what is output by input? Therefore, the gain is equal to I nu of L output by input, I 0, I nu of 0, I nu of L divided by I nu of 0 equal to e to the power gamma L. This is the gain, not gain coefficient, this is gain, and gamma is called the gain coefficient. So, gamma is the gain coefficient. Gain coefficient. So, what is the gain coefficient? Gain coefficient gamma is equal to V square or C by n. Let me write it as C by n, just because otherwise sometimes nu and V may get confused. So, 8 pi nu square into rho of nu, density of states divided by tau r into F e of nu minus F a of. I have already called it as gain, but when will it be gain? It will be gain if gamma is positive, and gamma is positive when everything here are constant, positive constant. This is a density of states, so it is a positive number. This is a number, it is a time, positive number, everything is positive. Only this can be positive or negative. And when will this be positive? This will be positive when probability of emission is greater than probability of absorption. And when will that happen? When will probability of emission be greater than probability of absorption? This is the condition that we have already derived, and so gamma is greater than 0 implies gain or amplification, and gamma less than 0, that is negative, implies loss, net loss or attenuation. and therefore, it is the sign of gamma which is important, and which will determine that it will be determined by this factor f e of nu minus f a of nu. And so, gamma is greater than 0 for f e of nu greater than f a of nu, and this happens when E f c minus E f v, the difference between the quasi Fermi levels is greater than h two. So, the separation between the quasi Fermi levels, if this is greater than h nu, then for all those frequencies we have gain in the medium. So, if you have a semiconductor here and light of radiation I nu, now I have put I of nu, if that radiation contains a spectrum of frequencies, I of nu, then, and if the material here is characterized by a band gap like this, energy band diagram I am showing. Now, let me show, this is E c, this is E v, and assume that in this semiconductor we have maintained E f c here and E f v here. So, this is the valence band, conduction band, and this is the E g. For h nu greater than E g, for all energy between, for all values of h nu between this, that is from E g here. So, E g less than h nu less than E f c minus E f v, for all frequencies nu such that E g less than h nu less than E f c minus E f v, we have this condition satisfied. It means, if I have radiation which is coming such that the energy difference corresponds to some value here, let us say h nu, then for this h nu which is greater than E g, but less than E f c minus E f v, we will have gain in the medium. So, if you pass a spectrum, then those frequencies for which energy corresponds to energy satisfies this equation, we will have gain in the medium. So, E f c minus E f v. So, this is the condition for gain. We have analytically showed that this is the condition for gain in a medium. This is equivalent, therefore, this condition, those of you who have studied atomic laser physics, you know that there you have to have n 2 greater than n 1, or a state of population inversion. So, a state of population inversion means n 2 is greater than n 1. This is the necessary condition for amplification by stimulated emission. And in the case of semiconductors, the necessary condition for amplification by stimulated emission is this one. So, there is an equivalent. It is incorrect to say that number of electrons in the conduction band should be greater than number of electrons in the valence band. That is not the condition. The condition is this. If you can maintain this condition, then all frequencies nu which satisfy this condition will get amplified. What happens to other frequencies? So, if we go here, for example, a radiation which corresponds to this frequency difference. So, this condition is not satisfied, and immediately that means f e of nu will be less than f a of nu, and therefore, this will be negative number, which means gamma is a negative number which corresponds to loss or attenuation. This will determine the amplification bandwidth. We will discuss this in the next class, the amplification bandwidth of the amplifier. So, our next topic will be laser amplifier, and an amplifier is characterized by gain and bandwidth and of course noise also. So, we will take a quick quiz, a simple quiz. This is a very simple quiz. The spontaneous emission spectrum of a particular semiconductor is given by, an expression is given to you, RSP of nu equal to K0 into x to the power half into e to the power minus x, where K0 is a constant and x is h nu minus E g divided by 4 k T. Obtain an expression for the wavelength at which peak emission would occur. Obtain an expression for the wavelength at which peak emission would occur.